Venkat sir, shall we start?
Yeah, I'm ready.
Okay, so we can start. Good afternoon to all. On behalf of Chipin Center, we welcome you to today's session. It is an honor to have Dr. H. Peter Opsey and Dr. Macros from IBM with us today. They will be leading a technical session today for all the participants. I would like to give a brief introduction of our speakers of the day. Dr. Peter Hofsey is a distinguished research staff member at IBM Infrastructure in Austin, US, and a part-time professor with a chair in big data systems at TU Delft, Netherlands. He has a doctoral degree in theoretical physics from the University of Groningen, Netherlands, and a PhD in computer science from the California Institute of Technology. He has contributed to the power architecture since 1996 with the first 1 GHz CMOS processor prototype, the cell broadband engine, and many more. Thank you, sir, for accepting our invitation. Now, I would like to give brief introduction about Dr. Paul Macros. Dr. Paul Macros is a retired IBM senior technical staff member in the IBM Linux Technology Center. He holds a PhD from the Australian National University. He has contributed to the Linux kernel for more than 20 years, particularly in the area of support for the power architecture. He also served as the architectural maintainer for the PowerPC architecture for 7 years. His most recent contribution to the Linux kernel virtual machine code supporting IBM Power processors. Thank you, sir, for accepting our invitation. On behalf of Chipin Center Select Bangalore, I warmly welcome you all, the participants, for joining the session. So now I would like to give the abstract of the talk, today's talk. During this presentation, a step-by-step walkthrough will be conducted to demonstrate how a full system can be built based on the open and free 64-bit OpenPOWER ISA microwatt processor, targeting the Arty A7 100T FPGA development board. For this walkthrough, compute will be leveraged to create the FPGA configuration data. Power PC architecture and the microarchitecture of the Microwatt processor were converted in previous sessions and will be briefly summarized. Additional background on the SoC architecture and the various tools used to build the Microwatt-based system will also be provided during the walkthrough. Now I request to IBM team to take over the session. Thank you.
So much for that kind introduction. So let me share the slides here. All right. So today, Paul and I will be speaking, but I'd like to acknowledge Madhavan Srinivasan, who's on, Jayakumar Singaram, and Pranos Edavor from CDAC, and for helping in preparing for today's session. So what we would like to do today is to provide you with a set of instructions that is pretty straightforward to follow on how to build your own Microwatt-based Linux system, leveraging the RT board. You don't have to take any notes. Everything in these slides and eventually a recording will be available at, or most of it is already available at this particular GitHub link. If you go there, you'll see one project, and inside that project is all the material that we will cover. Part of the reason for doing this is to try to create a set of instructions that is very scalable. So India is a very large country. And CDAC has ambitions to reach lots of students, researchers, and startup companies. And in order to do so, the instructions have to be pretty robust. So with that in mind, we restricted it to a very specific environment. So the instructions that we give are, well, I'll cover that in a second. So there were two prior sessions. I gave a session on the background of the power architecture, and Paul gave a prior session covering the microarchitecture of Microwatt. So as I mentioned, both of these sessions are available on YouTube, and these links are also included in the README in that project that I mentioned. So again, I would encourage you, if you write down one thing, write down this link. It's also in the chat in this meeting. So this is what that board looks like. You see in the middle there a not too big, 100 kilowatt FPGA. And to the right of it, you see a DRAM. The board also has an Ethernet controller, and then this is the USB port that you use to talk to the board, and it has a built-in FPGA programmer chip as well. And a flash. We're not using the other peripherals yet, but we will use the Ethernet as well as, of course, the USB to interact with this board. So as I mentioned, we wanted to create a set of instructions that is going to be pretty easy to use, so that this material could be scaled to a large number of students. And so we are pretty prescriptive in what is being used. So we are using the 22.04.4 LTS release of Ubuntu. And we recommend at least 8 GB of RAM and 100 GB of storage if you're doing your own system. And the instructions that we created assume only a minimum install of the operating system. So that will be true for many people. So a lot of there are quite a few dependencies of packages that you'll depend on, and we try to be explicit about everything you need. By the way, I did also build, especially the first steps, a number of times on a cloud instance. And if I get myself a 4 GB cloud instance, that works fine as well. The version of Vivado that we're using is 2024.1. I know that the build also works with older versions of Vivado. So if you're asking for help, we will ask if you have this particular version, but I think it is likely to work with the older version as well. And of course, you need the Arty board if you actually want to see it run on hardware. So there are a number of dependencies. So if you're using a CDAC account, and I believe that the attendees today were provided with a login to a CDAC account, you don't need to do this step, nor do you need to do a similar step to install various packages, because it will have been done for you. But if you're building this on your own Ubuntu system or a cloud instance, then you will need to do these steps. So there's a couple of steps here to make sure that the package manager is up to date. And then the things that are installed, the first one is build essential. So if you want to build things on your Ubuntu instance, you need the C compiler, the make tool, libraries, source package and bin utils, linker assembler, that kind of thing. So that's the first one here, build essential. Git, I didn't include another page on that, but that's just so you can get things from the GitHub repositories. And then GHDL, there's these 4 things all have to do with GHDL. So Microwatt is written in VHDL 2008, and the GHDL tool, compiles and includes a simulator for designs written in VHDL. And there are a few different backends for that. And it has a dependency on the Ada compiler, so you also need to install the GNU Ada compiler. And then finally, since most of you would not have access to a power system to build on, you would need and you would be typically working on an x86-based host machine. Now maybe a few years down the road, when we're successful and there's lots of smaller power systems out there, more of you can natively compile. But until then, if you're developing on x86 and you're targeting your code for the Microwatt power-based system, you will need a cross compiler, right? So a compiler that runs on the x86 system, but produces binaries for PowerPC. So it's a linker and loader, GCC and C++ compilers. So that's what those last things are. So with that out of the way, you'd be ready to actually build MicroPython. So you pull this down from the from the MicroPython repository, and there is a particular port for PowerPC, and you make that. So MicroPython is a version of Python that is small enough to run typically from the VRAM, the block RAM within the chip itself. So it doesn't really need external DRAM. So I'm not going to take you through these steps here. This I think is quite robust. If you have those dependencies resolved, we've tried it on a number of different systems and cloud instances. I don't think you'll have any trouble. So to the result of building MicroPython, you'll get a piece of firmware that you can install on the processor. So the next thing you do is you actually build the Microwatt processor. It's actually an SoC itself with GHDL. And again, instructions are quite simple to follow. So the top. So if you're want to dive in a little deeper and look through the VHDL and so on, the top file there is this core testbench.vht, and in this picture, I try to give an overview. It's not everything, I think, but these are the main components. So the core, so if you look at the test bench, it has an SoC in there, and then inside the SoC is the core, and then of course inside the core there are many components. There are several components in each of these, but I stopped at this level. The core is that 64-bit power architecture Microwatt core that Paul covered in a prior talk. And it's connected through this wishbone interface. This is a bus interface that connects the different components within the chip, based on memory mapping. So the core talks to everything else through that wishbone interface. If you're building MicroPython, then you instantiate your RAM within the chip in these FPGA block RAMs. So that's this block RAM component here. If you're building MicroPython for the Arty board, as we'll do later, then you actually don't use the VRAM. So you'll see that there is some command like memory equals 0 or something like that, no VRAM. And then you use the DRAM instead. And there's a debug interface. The syscon interface provides a whole bunch of MMIO registers that, for example, allows you to find out the version number and attributes of this particular instance. It has UARTs that allows you to talk to the board through a TTY type interface. It has a flash, so the flash is on the board, is used both to hold the bit file for the FPGA, but also the Linux image or Python image. Interrupt controllers and GPIO. So these are, I think, the main components, and each of those correspond to a VHDL file. So that gives you hopefully an idea of the structure here. So if you run this, you'll see it works. So this is running Microwatt in simulation. The GHDL compiled version of Microwatt. And my typing here wasn't super fast. But now it's actually started. So from this point, you're actually seeing the design run. And what you'll see here, so it gets to this prompt, and I ask it to do a simple calculation. And it takes a good while. I think you have to be patient here for a minute or so before it actually comes with an answer. And that, of course, is because this is now not running on actually hardware. This is the GHDL compiled version that is simulating the hardware. So every little component of the hardware, the next state of it has to be calculated, every cycle, and that takes that takes a while. So I'll let me kind of fast forward through it here. It does come up with the right answer, and I also I gave that help command. And indeed it all works.
I wonder if it's helpful to explain here that GHDL is actually a compiler that produces an executable, and what the executable does is simulate the VHDL that was given to. So it's not that exactly. GHDL itself does the simulation; it creates an executable that does the simulation.
Yeah. So I think one of the modes for VHDL is an interpreted mode, which is even slower. Right. So yes, indeed, this is using the compiled version of the hardware. But of course, within that compiled version, you're still maybe simulating is a bit misleading word, but you're emulating all the different things that have to happen inside the hardware. Yeah. Thank you, Paul. So then. And actually, if you go through the steps here, I think you can get through all of these steps in 15-20 minutes or so. This is really quite fast. Getting the things from even if you have to get the dependencies installed and everything, it really is pretty quick. Installing Vivado, which is already done for you if you're in the CDAC environment, that takes a while. Vivado is from Xilinx, the tools that you need to target the Xilinx FPGA that's on the Arty board. There's a web installer for it, which I think is some 300 megabytes or so, which you can download and then run the installer. If you actually want to pull down the package that has everything in it and then build it from there, that's by now is 107 gigabytes. So just downloading that takes a long time. So we're not going to do that here today. That takes too long. But we will show you the build on the Vivado tool. And again, within the CDAC environment, Vivado is already installed for you. Besides Vivado itself, you also need to install the Digilant, and Digilant is the vendor of that Arty board. It has some definition files that Vivado will need, and there's instructions on how to add that to your Vivado install, and these board files are also pre-installed in the CDAC environment.
Interesting, because I don't know that I actually have them installed.
I see. So you managed to build without it?
Yeah. Yes, because I think all the necessary constraints are actually in the Microwatt code.
In the micro, okay. All right, good.
Yeah.
Well,
Bad
that
thing
might
to do.
be that might be a superfluous step then. Yeah. And then there is a package manager, a hardware package manager called Fuse SoC. So this is, it's basically similar to how you would use Make to compile more complicated software projects. Fuse SoC is you can think of it as a hardware package manager, and it it understands various tools for building and simulating designs. And it understands hierarchy, and we'll take a brief peek at what the Fuse SoC file looks like from Microwatt. And again, Fuse SoC itself needs to be installed. It has some Python dependencies, so at least in my case, I had to do some updates there, and but again, in the CDAC environment, Fuse SoC is pre-installed. So this is actually how you build Microwatt. And at this point, I think I would like to ask Madhavan to show us how this starts. So Madhavan, maybe if you could take over the screen, and then we'll start the Microwatt build, and then we'll look at
I just took the privilege of starting it because it's going to take some time. So
So yeah, why don't you go ahead and start it, and then we'll look at that for oh, it's already running?
No, it's almost it's in the phase setting, so it's still building, but
okay.
It should complete soon.
I see. Is it possible to
yeah, exactly. So I just want to show them this is the Microwatt tool where he was also talking about the VHDL, different VHDL files. And for the Fuse, these are the steps that we primarily have to execute the infrastructure. So this is primarily adding the Microwatt library and also the path for the Fuse SoC. And then we have to use the UART 1650, which is part of the command line, and which is also can be added as part of the fetch from the Fuse SoC. And final command that we have to start to build the target for the Arty A7 registers. And I just took the privilege of starting this in the next window since it's going to take some time to start. Right? I just took the privilege and started that as part of this process, and it's writing the bitstream right.
Yeah, I think it's finishing up. So
Yeah.
and so let's let it finish up, and then maybe, I don't know if we can after that scroll back
Definitely.
a bit.
Yeah, definitely.
So the build using Vivado in the CDAC environment, I think it takes about 25 minutes, right?
Exactly. So it approximately 20 to 25 minutes to complete in the current environment that we have in the CDAC.
Right. So it's reasonable, I'd say. Yeah. So it should be finishing here in a minute, right?
Hopefully, yes. Yeah.
Actually, why don't you try to scroll up, and then we can jump back on.
Yes.
So maybe go see if you can find the very beginning of Right.
Yeah.
Yeah.
So, yeah, go ahead.
Yeah, very good. And what you see here, for example, I talked earlier about how Microwatt can either run out of the BRAM or the DRAM, right? So in this particular case, the BRAM size is set to 0, and it's using the so there's a Litex DRAM controller, SD card flash controller. So these are some standard components that connect to that wishbone interface, and also the Ethernet driver. You see it's pulling that in, the SD card. Okay, maybe you can scroll down just a little bit. Okay, keep going. Yeah, can we get that? And then, yeah, just keep going. And then what you'll see is it goes, through a number of optimization phases, right? So, it'll generate a net list. You can keep scrolling, and then it actually places that net list in the FPGA, does timing. It actually already does some timing before it does the placement, and then you'll see it go through a number of iterations to improve the timing. And I think in the end, you end up with the design in the order of 100 megahertz or so. So yeah, you can scroll again back to the very end. It will probably have completed by now. So there are, two lengthy steps if you're building everything from scratch. This is one of them. Oh yeah, there you see the netlist cleanup, removing redundant elements and things like that. And the other lengthy step is if you decide to build your own Linux kernel, and Paul will cover that in a bit. Yeah. Okay. So hopefully then, yeah, it's done. Yeah. All right. And also, if you oh, okay, yes, and then you can see the resulting bit file in that directory there. Yeah, great. And that is, in the end, when you're running it on the Microwatt chip, you need this bit file that configures the FPGA, and of course you need the software. So very good.
Yeah.
Thank you.
Sure.
And then I'll go back to my slides here. Yeah. All right. So we went through this step. Yeah, and this also the end here of that one. Okay, so then I'll pass it over to Paul, and Paul will talk a bit about building your own Linux for the Microwatt SoC. Go ahead, Paul.
So basically, what you need is a current upstream kernel, or you can use a stable image. I've actually been building kernels from 6.8.8 and whatever. So, but you need a configuration file, which you can get from the Arch PowerPC configs directory. There's a Microwatt defconfig, which should be fine, and then you can tweak that. You can add extra drivers or whatever, just like building any Linux kernel. So then, what you need is the cross compilers that were installed earlier, and you need a command line of the form make, and you need to set to arch, ARCH variable to PowerPC, and you need to set cross-compile equals and the prefix for your cross-compile tools, which will be PowerPC 64LE dash Linux dash GNU dash, yes, just like that, like you see on the screen. You can have an init ramfs if you want, or you don't have to have an init ramfs. Either way works. So you do that make, and if you've got a reasonably powerful machine and you use the -J flag, it doesn't actually take all that long. Sorry to contradict you, Peter, but on
I
my
waited for a while. It took me longer than running Vivado, but my machine was not. I did it on a little $200 PC that I bought for this purpose. So it was a pretty inexpensive machine. Yes.
Well, I'm sure it only takes a few minutes on if you've got a 6-core Intel machine, it should only take a few minutes. Anyway.
Okay, it took a lot longer for me. Yeah.
Okay.
Yeah.
So depending on how powerful your machine is, it might take a different amount of time. And what you get out of that is you get this DTB image.microwatt.elf, and that is actually a file that's got, it's like a Z image that you would have on other architectures, in that it has a compressed kernel and a little wrapper to decompress the kernel, and it also has a device tree. Many of you are probably familiar with device tree from ARM or MIPS or other architectures that also use device tree. It was invented first on PowerPC by a guy called David Gibson, by analogy with what OpenFirmware was doing, but then got popularized and taken and used on many other architectures. And in fact, in particular, ARM uses device tree. So if you've done embedded ARM Linux work, this should all be fairly familiar. Anyway, so you get that DTB image, and so then what we're going to do then is to put the bit file and the DTB image onto the flash.
Yeah.
So these two flash Arty. So the bit file goes at offset 0 in the flash is 16 megabytes. The first 4 megabytes is reserved for the bit file, and then the remaining 12 megabytes can be your kernel. Or, I mean, it doesn't have to be a kernel. It can be essentially any 64-bit PowerPC ELF file that can then just run, basically on the bare machine. But if you're not on Linux, then this is the most convenient way to do it. One of the things I want to do is to get a U-boot that runs on Microwatt and that I can distribute. I actually have one that was developed inside IBM, but then I left IBM and it was never kind of released, so I'm not sure of it. Perhaps, Peter, we could have a talk about that. Whether I can release this U-boot port that I did while I was at IBM. Anyway, having U-boot there is quite convenient if you want to be able to net boot or choose different images or whatever. Anyway, so you put the bit file there, you put the ELF file that you want to execute, and then basically there's a piece in the middle that you don't see because it's kind of baked into the process, but there is a bit of code, a bit of PowerPC code that does DRAM initialization and some system initialization, and it's got an ELF loader that looks in the flash and loads what's in flash into DRAM and executes it. So that's the piece that might be missing for some people, and it does what you can see there. So that is all embedded into a block RAM, despite the fact that you said no BRAM and memory size equals 0, you still get a block RAM for DRAM initialization and system initialization. Anyway, so at this point, you should be able to boot a Linux kernel. But then the question is, what is it going to run when it boots? Where's it going to get its root file system? So then that is where we get into build root as being a way to create yourself a little distribution that's got all the user space for your Linux kernel to run. So that's the build root bit. And that does take a long time. That takes a very long time because it's going to pull down the source code for all sorts of different packages for user space programs and build them and put them together into a file. And then you can take that and you can turn it into an archive that you use as the init ramfs for your kernel. So that's one way to get going without any external storage. You use a RAM file system with your root and that RAM file system, and then you've got BusyBox and the other familiar kind of things in there that can then give you a shell prompt and let you do ls and set up networking and all those kind of good things. I will mention that the default build, as of the master branch of Microwatt, has got support for an SD card interface. And what you do is you buy one of these PMod SD cards, and they're like $10 or something. Right.
Oops. Yeah, there's
actually. So you got one?
Well, yes, I have it lying right there. I'm sorry, it's not. Oh, here it is. This guy.
Yeah. So you buy this, and it's like, I don't know, $5 or $10 US, and you plug it into the current thing is the JA PMod port, so like that here, and then you can put a file system on a little micro SD card and boot off that. So if you're doing that, you don't need the init ramfs. You could do your build root thing, get the file system image, put that onto an SD card. Many PCs have got a slot for an SD card, or alternatively, you can buy a little USB adapter that lets you write to your SD card. So you can put the file system onto it, then put the card into the adapter, and then you can boot Linux from that with that as your root file system. So that works quite well. It's also possible to use an NFS root. If you've got an NFS server, you can give the appropriate command line arguments to the kernel to say, this is the address of the server and this is the path to the root file system, and it will do an NFS mount to mount that file system off your server. And if you have an NFS server, that's really quite convenient, because then you can also get to your file system from other systems as well. So you can see what it's doing, kind of thing. I'll also mention that the sockets in the middle, are kind of either side of the FPGA, are suitable for
these things. Oh, I see these ones.
Yeah. Yes, they're suitable for connecting shields that you might find for Arduino projects. So we've got a local electronics retailer that's got various Arduino related items for sale, and one of them was this little LCD screen that you can see. So I've got an LCD screen plugged into the shield. Now, it's also a touch screen, and there were various complications because of the 200 ohm protection resistors that it has. But with some modifications to the shield, I managed to get it to work. So I've now got a 240 by 320 color LCD display on my Arty. So you can do all sorts of interesting things.
Great. So actually, I thought maybe it's fun to actually see it boot. Yep. because that is, I was impressed by how fast it is. So
this is the wrapper. It was decompressing. Okay, now we're booting.
Yeah.
So you'll see, first of all, the firmware, that built-in initialization firmware that I was talking about will print some basic information about the system, and then initialize the SD-RAM, and it's a bit of a boast about how it's tuning the, whatever, the communication paths to the DRAM. And then it gives you memory speed, so a couple of 100 megabytes a second. So then it looks in the flash memory, it says copying segment 0 that's ELF segment. So this is analyzing the ELF file, and it copies the ELF file out of the flash into DRAM. Then that's the wrapper that runs. The wrapper decompresses the main kernel image. So you'll see decompressing up the top there, third line from the top, decompressing, and then it's decompressed 22 megabytes, I think, is what that hex number means. So it's decompressed 22 megabytes in a few seconds, and then it starts the kernel, and then the Linux kernel boot messages. Okay, so you got a 6110. I see something, and it actually boots reasonably quickly. For a 100 megahertz processor, it doesn't sort of feel really sluggish.
I was quite impressed, I have to say. Yes. Yeah, and then also you see, I did have the Ethernet port plugged in, right? So it actually obtained an Ethernet piece, of an IP address.
Yeah.
And then it gets to the login prompt. And yes, earlier, I was kind of glomming build root and Linux together. It was build root that took the inordinate amount of time.
Yes,
yes.
I definitely
not the Linux kernel itself.
But,
yeah.
With build root, you set it going, and then you go away and you have a cup of tea or something, and you come back. Yeah, but it's really quite convenient, and it works and it does the job. So
and right, and just so because I know we have a bunch of people in the audience that I think are not software people by any means. So really the only thing you need, right, is this image, right? So you don't you don't have to. I mean you can build the beat build root and kernel yourself, but I also put them somewhere on Google Drive, so you can you can pull them down, and these commands are in the instructions. And then
that DTB image that has your build root as an init ramfs, does it?
Yes, it has it inside.
So then
because
right.
Yeah. So you right. I mean, it's a little bit cut off here, but of course in the actual instructions this line continues. But you see here is the init ramfs source, right? Yeah.
Right.
And it ends up in the in that Microwatt ELF image. Yeah.
Yes. In fact, the init ramfs ends up actually in the VM Linux binary, and then the VM Linux binary gets compressed and included in the DTB image wrapper.
Right. And then it copies that compressed piece, as you described, into later. Good. So I think we covered all of it. Oh, I know you used Minicom, Paul, for me for a reason that I haven't really figured out. I mean, I have the basic settings the same, but for some reason GTK term worked for me and Minicom didn't. So.
It doesn't matter.
Yeah.
It's just a terminal emulator,
right.
whichever one you want to use.
Yeah.
I mean,
yeah. And then what I imagine that quite a few people might like to do is if you're thinking of using this as an edge kind of device, a network attached something, then it's as Paul described. I mean, it's a Linux system. You can you can mount file systems and everything, but if you're building an embedded type edge device, then I think one of the likely things that you might be doing is to actually enable SSH. So there's a couple commands there. I left that page out. There might actually be a good excuse to go look at the So this is the, these are the instructions. We got all the way down here. So if you set the root password and you do this command, udhcpc -i ethernet 0, then after that,
I thought
I'm
your
sorry,
Ethernet came up automatically.
I'm not sharing my screen, I think. Let me.
I thought we saw on the boot log that the Ethernet was actually brought up automatically.
Yeah, the Ethernet was brought up, but not the. You can't SSH to it when it comes up. You have to for some reason you have to set a root password and you have to do this command to actually be able to SSH to it. So again, this here, all the instructions are here. This is at that in that hostc HP, right? There's only one project. You go in there. The slides of today's session are right here, right? It's taking a while to parse it, right? So you can find that. And I also put the DTB image firmware and bit file over there. All the instructions are here, including instructions on how to install Vivado and so on. And then if you enable the SSH by doing those couple of commands, then back to this. Oh, I did have the commands here. Yeah, sorry.
I'd be willing to bet if you plug that SD card adapter into the JA PMOD, you'd see the file system.
I see. Yeah. No, that I think would be very useful because even when you're creating an embedded device, of course, if you if you have everything in DRAM, then it's lost, right? You'd have to create a new thing to put in the flash, and that's kind of onerous. So yes, I do think that micro SD card is a very nice addition that most people would use. And then after you do this, you can actually SSH successfully to the Microwatt system. So now you have a network attached system. And one thing to be aware of, I don't know, I'm doing it from my Mac, and my settings are such, because we are going from DRAM every time, and it doesn't remember stuff. It generates a new random number every time. So if you SSH twice, you'll get this warning, that the key is different. So there is a file, and this would be on your Mac or PC, the one that you're using to SSH to the Microwatt system. And there's a known host file, and you basically have to go in there and delete, the line that is associated with that address that was assigned to your Microwatt system by the DHCP server. But if you do that, then it all works fine. And I had actually created a little hello file, and you see it. So that all works. So what I'd still like to do is indeed, as Paul mentioned, add the instructions for how to connect the micro SD, and then also this will just update the online instructions. For a future talk, I hope that we'll do something where we use Microwatt as a microcontroller for something. There's already a few people thinking about different projects. And I think that'll be interesting, you know, to see how you actually use this to control something else, probably via the GPIO pins or something like that on the Arty board. I'd also, I hope we might have a future session, because we had a few questions about this in a prior session about you know, how you add a custom instruction to do something, right? And of course, there's specific ways of doing that so that you remain compliant to the power architecture. But there are, you know, there's a space in the opcode map where you can add your own custom instructions. So I think that would be a very interesting thing to do. And then, you know, and this kind of has my main focus. I know that in this particular program, you know, while building things on FPGAs is just wonderful, and you know, as we saw, I mean, if you can boot, if you can go through the build route and boot Linux in under 20 seconds, you know, this is already a very useful thing, obviously, on an FPGA. But if we could build hardware, you know, it'd probably be again a whole bunch faster, and if you build enough of them, a whole bunch cheaper. So we'd like to walk the path, which I know Anton Blanchard, who is one of the original creators of Microwatt, has already walked this, and actually you know, go from the design that we have now for the FPGA to an actual tape out to a fab. You know, ideally the India fab, but there's also you know, other fabs that are fairly easy to target. So that's something that we'll be working on for the future. So with that, I think we have time for questions.
I'd just like to say that these PMOD ports, if you're trying to do a microcontroller, these PMOD ports are very useful because you can, there's all sorts of PMODs you can attach, or you can make your own. It's just a very simple interface. And I've actually done things like I did a programmer for some old programmable logic chips that I have that plugs into there, and I did some custom logic that serializes bits and sends them out. And I mean, yes, you can do it all with GPIOs, and there are 32 GPIOs supported already, and you could add more very easily. But then sometimes it's cute to create a bit of custom VHDL to simplify the software, and
Right.
And you can do that very easily.
Yep.
So the participants can unmute themselves and can ask questions again.
Oh, one thing that I didn't mention very clearly, I think, is you know, because we do anticipate that there are going to be quite a few people actually doing the builds, etc. If you have a problem, if there's an instruction that seems wrong, or you have a suggestion or anything like that, what we ask you to do is open an issue. So if you, let me share my screen again. If you go up here, see, you can, there's a button that says issues. So if you have a problem, a suggestion, question, please use the GitHub issue interface to do that. That has the benefit that you know, everybody else can see the issues as well. And you know, of course, this is just an elaboration of you know, the original Anton Blanchard you know, this repository here, right? So if there are comments or issues that are more fundamental to the design, not the specific instructions that we created, this is a more appropriate place to interact with that. But if you have questions about the set of instructions that we created for this particular environment, please raise those questions here, and that would have the benefit that everybody that tries this, can see that the problems and solutions that other people had, and of course, if we update this, it'll benefit everybody. So because we were a little bit worried about, if we might end up having 1,000 people or so try to do this, there could be quite a few questions. Now we've tried to make this robust, but one can always anticipate that there'll be something.
Any questions from the participant side? Can you unmute yourself and can ask?
Yes, good evening.
I can hear you. Yeah.
Yeah, sir, can you process any type of image by Arty A7? Are there limitation to process type of image?
So I'll ask Paul to talk about interfacing cameras and things to an Arty A7. But from a processing perspective, of course, yes, it could process anything, but it's the question is how deeply you want to process, right? So if you are trying to build, say, a neural network or something to analyze an image, you would probably end up in a situation where you want to build yourself, some kind of an accelerator for that particular purpose, because you could do it on, in a piece of C code or something that you run on the processor as it is, but for something like a deep neural network, it would probably be too slow. So I don't know, Paul, if you want to comment about talking to cameras or things like that.
Yeah, I haven't done that kind of thing. Was the questioner asking about an image in the sense of a picture, or were they meaning an image in the sense of like a binary, program file? I wasn't clear about what kind of image.
So that was the question. I interpreted the question as being about pictures, but was it indeed about pictures, or was it a question about like binaries? So if the person who asked the question could please clarify. You may have gone back on mute, so I don't think we can.
If it's about program files, then it would need to be a PowerPC, executable.
Yes.
Using PowerPC instructions, because that's what it is. You can't. It won't execute like an ARM binary or a MIPS or RISC-V or whatever.
So that's what those cross compilers, for example, are for, right? So if you need to generate code for this, you would use these same cross compilers.
Right.
If you're doing your development on an x86 system, that is. Yeah.
One thing that perhaps if people do want to compile a program to run on the build root, in the build root environment, it's useful to note that inside the build root directory, you will find cross compilers that the build root process has built. Now, the ones that you installed from your distro are not aware of any runtime system, so you'll have a restricted environment if you use those ones, but you need to use those for the kernel. If you want to compile a user space application to run under the build root, in the build root file system using the build root C library and everything else, then you find the cross compiler that build root made and you use that. And that way you can compile a binary that you can then put into the build root image or access off a file system or whatever, but you can run it from the BusyBox than the BusyBox from the build root environment. So it'll be in your build root, like /build root /output /host /bin. If you look in that directory, you'll find cross compilers that would be better for compiling an application to run in the BusyBox environment.
Great.
Hey, Paul and Peter, there are a couple of questions in the chat regarding whether we can have different targets or these targets are specifically only for Arty. So,
sorry, I didn't catch that.
There are a couple of in the chat primarily asking whether do we have support for other boards other than Arty? That's one. And also, is there the kernel config supports for any other board other than Arty 7?
The kernel shouldn't depend on the board all that much, although you might need to tweak the DTB. So if you're doing it for a different board, you would look at Arch PowerPC boot DTS microwatt.dts, I think is the path, or it might be DTB / anyway, you find the microwatt.dts file, which is the device tree source, and you may need to tweak things like the amount of RAM, or if you put things at different addresses. But generally speaking, you don't have to change very much. Yeah. You shouldn't actually have to change the kernel itself, and you may not even have to change the device tree. As to using a 200T or a different Xilinx board, yes, you can. What you'd have to do is you'd have to look at the file FPGA / Arty A7.xtc, and you may need to change some of the constraints in there. For instance, Microwatt will run on a CMOD A735, which is this little thing. So that's another Xilinx FPGA board. It's actually got a much smaller FPGA on it, and this one is not really big enough to have the full Microwatt with the floating point unit, but you can fit Microwatt without the floating point unit on it quite happily. So that you'll find in the FPGA directory in the Microwatt source, you'll find a file called toparty.vhdl, and I think there's a top CMOD. I should just check that. But anyway, you'll find a top level file and a constraints file. So those are what would be different between the Arty A7-100 and some other FPGA board. So where are we? Yes.
The question about AES, whether it supports cryptographic algorithms. So I think it's a little bit similar. You want to go take it?
Sure. What you need to do is design the logic to do the AES calculation, and you need to write the VHDL basically to say these are the registers and these are the logical functions that join the registers and control what happens between one clock cycle and the next. And certainly there's nothing to stop you either writing or finding somewhere else an AES implementation in VHDL and importing that into Microwatt and hooking it up to an instruction and making yourself an AES instruction. That's all perfectly doable, but it's not. I mean, the thing about an FPGA is kind of it's all these resources, but nothing's connected together, and you need to say how all these resources need to be connected together in order to make the circuit that does the AES calculation, which is terrific, great fun. Yeah. But it's not just handed to you on a platter typically.
And in general, of course, right? I mean, it depends a little bit what you want to do with the AES algorithm, whether you can just run it as software or whether you'd be inspired to add a piece of hardware through a special instruction or you know, a memory mapped accelerator unit or something like that to the Arty system. But yeah, I think adding an AES instruction or you know would be an interesting project to do.
Yeah, of course you can just use PowerPC instructions and do it in software, but if you want to do it faster, you would need to design the hardware that does the computation and hook that up into the Microwatt core and then use it. So yes, the question about other FPGA boards is that you look in the FPGA directory in the Microwatt project, and you find these top dash whatever .vhdl, and they are different for each. That's what customizes it to a specific FPGA board. So you'll see ones there for a Nexus video board and an Orange Crab board and a Wukong board and other things as well. But I think, Peter, you were saying that we want people to basically all use the same environment so that the instructions can be fairly simple and robust.
And of course, you know, I don't want to discourage people from using other boards or other things, right? But in that case, you know, I don't know that given the volume of students that we expect, that we can sign up to provide support, right? So again, you know, the original project is, you know, this Anton Blanchard Microwatt project. And you know, I'm certainly not trying to take over that project. That is the project. You know, the instructions that we did is just to try to make sure that for a very specific environment, you know, and we settled on the Ubuntu 22.04.4 long-term support, and together with CDAC, we selected the Arty board because we know that many affiliated institutions, you know, have that particular board. So we settled on those two to you know, to support you know, through this program at CDAC, right? So future talks will also, you know, be based on that particular environment. But of course, you know, if you are a little bit less dependent on getting very detailed instructions, then by all means, you know, and if you go, you know, as Paul described, if you look at the various FPGA boards and so on, there are many to choose from that should work, you know, with
yeah, I mean, you can even go for an ECP5 like this one.
Ah, okay.
That's a lattice ECP5, so it's not even a Xilinx.
So I've learned, Paul, that at least if from the US you try to sell lattice FPGAs to India, you run into hurdles.
Really?
Yeah.
But the Xilinx is fine.
The Xilinx is fine, but if you look at there's an export control number associated with the lattice FPGA that throws up roadblocks. It's silly, but yeah, you know, that is also one of the reasons. This Arty board is you know, an export language. It's EAR 99, so you can send it anywhere.
Right.
But even small lattice FPGAs seem to require some kind of an export license.
Okay, I believe you.
It's
Seems very strange. Because I would have said that the Arty A7
is a bigger FPGA.
more powerful than the ECP5.
I know, I agree, but yeah, don't ask me why.
Okay.
Yeah. No, I you know, if you wanted enough of them and you applied for an export license, I think you probably would get one, but that's a lot of trouble to go through. Yeah.
Any other questions from the participants? So
There's one that says a typical example that exploits the full resources of this that proves this is advantageous. Any example could be spelt. Not sure what that exactly is asking.
I think they're asking if there is, you know, if you have a choice of things. So if you target an FPGA, right? So first of all, if you target an FPGA versus building a piece of silicon, you know, the trade-off that you're making is that an FPGA is more expensive and slower, right? Sometimes by about an order of magnitude, right? So, you know, I think this is a very powerful, very, very well-performing 100 megahertz processor, but it's a 100-ish megahertz processor. I do think, and you know, I don't have hard data on this, but you know, the Arty core, it's a 64-bit core, and that has you know, in certain situations that has advantages. Also, the power instruction set is I think a very well-crafted instruction set. In his previous talk, Paul also explained how some of the most recent additions to that instruction set, like the ones that allow for you know, 64-bit instructions and, you know, longer distance branches and things like that, are incorporated in this as well. So I anticipate that the you know, that the performance for you know, for a core 64-bit core of this size is actually quite good. But I don't have hard data on that, comparing it to other things. But I can tell you, I was really, the first time this thing booted, I was blown away by how quick that all went. And then, you know, outside the core, yeah, it's just an FPGA versus other things, right? So if you, I think it depends a bit on the size of the thing that you're building, but if you expect to need 10,000, 100,000 instances of something, then you might start, and maybe for something this small, it's probably maybe in the 100,000 plus range, then you start thinking about building silicon rather than using FPGAs.
So one thing that might be interesting in this context is the Libre BMC project, which is a project that was aimed at making, like, the BMC, the baseboard, whatever it is. It's a little controller in every server processor. You know, every server computer has a little processor that is responsible for controlling power and a number of other boot type functions. And typically these are little ARM processors. And so this project was looking at, would it be possible to use something like Microwatt on an FPGA as your BMC for your server? And this would have a number of advantages, particularly if you are fairly paranoid about code that might have been inserted in the supply chain. If you're worried about supply chain attacks on the security of your processor, to be able to inspect the code that goes into an FPGA, you know, lets you inspect the system from top to bottom and even rebuild the code and reflash the bit file and whatever. It makes it a much more transparent system. And it turned out that Microwatt as a BMC did actually perform reasonably well and was able to do all the functions that were required. It also has the opportunity of adding extra cryptographic type checks to extend the scope of your trusted boot process and that kind of thing. You can have cryptographic verification, you know, crypto hardware built into the FPGA that you might not be able to get from your BMC vendor, which is typically almost always A-speed. So anyway, this project was looking into the idea of using an FPGA as the BMC, and got quite a fair distance with it, I believe. I was involved with some initial investigations that were done here to just try the feasibility. And what we did is we actually replaced the BMC on a Power 9 server with an Arty board with a special adapter that I did. So we had an Arty board and an adapter that plugged into the socket where the BMC normally plugged into in this Power 9 server. And we were able to run OpenBMC on the Arty board on Microwatt and use that to initialize and boot the Power 9 processor. So that's one case where having an FPGA gives you a level of transparency and customizability that may actually be very useful.
Welcome to the new world of it.
Well, I'm sorry, that was a bunch of noise there. But apparently there's a video on it, a demo is showing the Power 9 server with the Libre BMC thing.
Yeah. Okay. So they did a custom card with the FPGA that plugged into the. One of the reasons we chose the Power 9 server was that it actually had a socketed BMC, and in many cases they don't. Right? They just have the BMC soldered onto the motherboard. But the Power 9 server had a socketed BMC, so it was a separate card that plugged into a socket. So we were able to make a different card that plugged into the same socket with the FPGA and put Microwatt and use it to run the OpenBMC code. It turns out that the A-Speed BMC was actually running a derivative of OpenBMC already, so that was fairly convenient. Anyway, we got it to work, and we got it to turn on the Power 9 system and boot it up, and it didn't seem to be horrendously slow compared to the. I mean, it wasn't. I don't think it was as fast as the A-Speed, custom silicon, but it wasn't unbearably slow either.
I put the link to the YouTube in the chat here.
So, any other questions from the participants, if there are? So, I guess there are no questions. So, once again, thanks to our honorable speaker, Dr. Peter Hopsey and Dr. Macros from IB. Your expertise and insightful talk have enlightened us with ideas that will carry forward. Thank you for your time and your dedication for making this gathering a memorable one. We are immensely grateful for your presence and your contribution. Thank you very much, sir. I hope all the participants are benefited from the session. Thanks to all the participants for joining the session. Thank you all.
Thanks so much for hosting us.
Yep, thank you.
Bye-bye.
Thank you.
Thank you.